We are doing today a Wolfram Physics project. I should probably bookmark these. Yay. Technical introduction. So, what are we doing today? We're taking a look at the path integral stuff, see if that's a good path to go down to as next. I did the basic concepts of quantum mechanics, quantum formalism, and quantum measurement. And then I took a sneak peek at the operators as well. But then I think here's where I kind of found a bit of the first friction in terms of um, because there's a correspondence. This is something we'll go in probably at the very end. Again, just keep in mind the goal, which is learn about quantum mechanics, right? Like I can't. The project is so wide that it just goes, I think, in too many directions. Um, and I'm not saying that I wouldn't like to go into general relativity and stuff like this. Um, I love to, but let me see. Is this currently streaming? Because that tells me that it is streaming, but I don't see the in the app. Oh, there it is. Just a bit delay. Okay, good. So uh, this was in quantum formalism, I think, path integral. And I just want to go in here because it's a direct reference here, right? In terms of understanding how the evolution is modeled here. Um, and maybe just so path integral versus what? Versus Hamiltonian? What are you comparing that with? I'm not so sure what is the. Wanted to understand a bit more what the comparison, or like what is this an alternative of? The path integral formulation is a description of quantum mechanics that generalizes the action principle of classical mechanics. It replaces the classical notion of a single unique signal trajectory for a system with a sum or functional integral over the infinity of quantum mechanically possible trajectories to compute a quantum amplitude. Okay, so it's a it's a description of quantum mechanics. Um, there's a series on quantum mechanics in the Wikipedia. Look at this. Oh, okay. That is something that I should definitely bookmark as well. Um, integral is no longer rigid in space, but a space of functions. A functional integration is a collection of results in mathematics and physics where the domain of an integral is no longer a region of space, but a space of functions. Functional integrals arise in probability, in the study of partial differential equations, and in the path integral approach to quantum mechanics. So that is one approach to quantum mechanics, but is it an alternative? Is an alternative to? That's what I wanted to go through today. Although that is just, it's probably too heavy, but we'll see where it goes. And I don't have so much time today, but I'll try to get to the point. Sometimes when you don't have time is when you learn the most. So so let's just go straight in. But I think this is an alternative to the Hamiltonian model, to Schrodinger's equation, right? So path integral versus Schrodinger equation. I think that is. So Schrodinger equation is the diffusion equation with an imaginary diffusion constant. What is the diffusion equation? And the path integral is an analytic continuation of a method for summing up all possible random walks. Analytic continuation. Diffusion equation is a parabolic partial differential equation. A parabolic partial differential equation of many microparticles in Brownian motion. Blah. Written as these were as the density of the diffusing material. It's a diffusion. Okay, so it's a diffusion equation. I don't know exactly what that means, but I guess what it's saying is that it's an equation that describes some sort of like a diffusion effect, whatever that might be. Interesting. So let's get going here. Let's zoom in a little bit. The notion of path integral originates in and is mainly used in the context of quantum mechanics and quantum field theory. Also, so quantum field theory versus quantum mechanics. Like, what is the difference? What is more fundamental? Quantum field theory is a theoretical framework that combines classical field theory, special relativity, and quantum mechanics. Okay, so that is a bit of a the particle fields are quantized. Okay, so we're talking about fields, which is something that we haven't touched at all. The notion of path integral originates and is mainly used in the quantum mechanics, quantum field theory. But it's used in both, right? Okay, where it is a certain operation supposed to model the notion of quantization, but I don't know what quantization is. So by quantization is meant some process that reads in a system of classical mechanics, or rather of pre-quantum data in the form of a Lagrangian action functional and or phase space equipped with and returns a corresponding system, quantum mechanics. What? What? Um, what is the quantization? It's like all these definitions. Hi, Study. Yeah, I can't. As I said many times, I really don't plan the streams. Yeah, I just wanted to do it now. Quantization. Or mapping input values from a large set to output values in a smaller set. Okay, so this is the process of, it's like discretization or something. Yeah. I'm supposed to model the notion of quantization. So path integral is uh, it's a certain operation that's supposed to model the notion of quantizations. It's supposed to model this transformation, or the idea is that the quantum propagator in FQFT, the value of the functor, I don't even know what a functor is, on a certain cobordism is given by an integral kernel, where what the fuck is all this stuff? It's something like the integral of the exponentiated action functional, ugh, and calls this the path integral. Well, that actually was under construction. That is too technical. The idea goes back to Richard Feynman, who motivated the idea in quantum mechanics. In that context, the notion can typically be made precise and shown to be equivalent to various other quantization prescriptions. Kind of theory encoded by an action functional should be disregarded the fact that Feynman-Kac formula. elementary description in quantum mechanics. A simple form of the path integral is realized in quantum mechanics, where it was originally dreamed up by Feynman and then made precise using the Feynman-Cach formula. Most calculations in practice are still done using perturbation theory. See the section blah blah blah. The Schrödinger equation says that the rate at which the phase of an energy eigenvector rotates is proportional to its energy. The rate at which the phase of an energy eigenvector rotates is proportional to its energy. Therefore, the probability that the system evolves to a final state after evolving for time t from the initial state is this. So, okay, so here we're talking about evolution probabilities. Chop this up into time steps and use the fact that the integral, you get all this stuff, which I have no idea how to read, and assume we have the free Hamiltonian. Looking at individual term, we can insert a factor 1. Blah, 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 blah. Okay. That is way too deep for me at the moment. Maybe we should start by trying to understand better the Schrödinger equation. I don't know. Let me try to see now if I can find some easier introduction to path integral. So quantum mechanics path integral introduction. I'm currently just trying to find, ways to. I'm trying to find an anchor where I can then kind of start going up. So I'm really just digging a bit deeper into all these. So I was looking at these. No, I was not. Did I? No, but maybe that's actually good enough. Although I would never say that Wikipedia is a good point to start because usually it's quite heavy. But let's give it another try. So the path integral formulation is a description in quantum mechanics that generalizes the action principle. It replaces the classical notion of a single. This formulation has proven crucial of theoretical physics because manifests Lorentz covariance, time and space. Unlike previous methods, method allows to easily change coordinates between very different canonical descriptions. Another advantage is that it is, in practice, easy to guess the correct form of the Lagrangian of a theory, which naturally enters the path integrals for instructions in time. Than the Hamiltonian way. Possible downsides of the approach include that you need 30. This is related to conservation probability. The probabilities of all physical possible outcomes must add up to 1. Subsequent formulation, the approach has been proved to be equivalent to other formalisms of quantum mechanics and quantum field theory. Thus, by deriving either approach from the other, problems associated with one. Okay, so it's something that can, it's equivalent to the Hamiltonian stuff, and the basic idea of the path integral formulation can be traced back to Norbert Wiener, who introduced the Wiener integral for solving problems in diffusion and Brownian motion. This idea was extended to the use of the Lagrangian in quantum mechanics by Dirac in 1933. The complete method was developed in 1948 by Richard Feynman. Some preliminaries were worked out earlier in his doctoral work under the supervision of John Archibald Wheeler. The names sound familiar. The original motivations stemmed from the desire to obtain a quantum mechanical formulation of the Wheeler-Feynman observer theory using Lagrangian rather than Hamiltonian at the starting point. Okay, so let's get into these. Quantum action principle. Let's say what is the structure here? Path integral. Famous interpretation. So maybe we can do these two. And then path integral and quantum mechanics. Time slicing, path integral, free particle. And this is a formalism that tries to capture the dynamic part of quantum mechanics, right? So how 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 does the system evolve, so to say. Sorry, give me a second. I'll be back in a second. Back there. The basic, where was I? Back here. In quantum mechanics, as in classical mechanics, the Hamiltonian is the generator of time translations. This means that the state at a slightly later time differs from the state at the current time by the result of acting with a Hamiltonian operator. That kind of makes sense. Multiply by the negative imaginary unit. So there's the Hamiltonian operator, which basically tells you how the system evolves, right? So you apply that operator, multiply by the imaginary unit minus I, and then you get kind of the next state of the system. For states with a definite energy, this is a statement of the Broglie relation between frequency and energy, and the general relation is consistent with that plus the superposition principle. I have no idea what this is. The Hamiltonian in classical mechanics is derived from a Lagrangian, which is a more fundamental quantity relative to special relativity. The Hamiltonian indicates how to march forward in time, but the time is different in different reference frames. And so the Lagrangian is a Lorentz scalar, while the Hamiltonian is the time component of a 4 vector. So the Hamiltonian is different in different frames. Yeah, because I guess it's purely kind of relative, right? Like it seems to make sense. It's relative to the observer, right? How the system will evolve. And so if you take a look at the system from another reference frame, then the Hamiltonian must be different because you'll perceive the evolution differently. Um, this type of symmetry is not apparent in the original formulation of quantum mechanics. The Hamiltonian is a function of the position and momentum at one time. Position and momentum at one time. And it determines the position and momentum at a little later. The Lagrangian is a function of the position now and the position a little later. Ah. Okay. So the Lagrangian, but how is that? So equally for infinitesimal time separations, it is a function of the position and velocity. Ah. So the relation between the two is by a legendary transformation. Legendary transformation. Involutive transformation and the real value convex function. And the condition that determines the classical equations of motion, the Lagrange equations, is that the action has an extremum. In quantum mechanics, the legendary transform is hard to interpret because the motion is not over a definite trajectory. In classical mechanics, with discretization in time, the legendary transformation becomes this, where the partial derivative with respect to q calls, okay, I don't know, and the partial derivative now is with respect to p at fixed q. In quantum mechanics, a state is a superposition of different states with different values of q. Q being momentum, I guess, or different values of p, position. And the quantities p and q can be interpreted as non-commuting operators. The operator p is only definite on states that are indefinite with respect to q, so consider two states separated in time and act with the operator corresponding to the Lagrangian. If the multiplications implicit as matrix multiplications, the first factor. And so it takes the Fourier transform in Qt to change bases. And so it takes the Fourier transform in Qt to change bases to Pt. That is the action on the Hilbert space. I don't know. The age factor contains all the information. It pushes the state forward in time. The first part and the last part are just Fourier transforms to change to a pure Q basis and to a P basis. Another way of saying this is that since Hamilton is naturally a function of P and Q, exponentiating this quantity and changing basis from P to Q at each step allows the matrix element of H to be expressed as a simple function along each path. This function is the quantum analog of the classical action. This observation is due to Paul Dirac. That one could square the time evolution operator and then that is already dense as well. Quantum action principle. Okay, but I get it. The difference being that the Hamiltonian is based on is a function of like two static values, right? Like the momentum and the position, while the Lagrangian stuff, which is then what the Lagrangian is a bit more fundamental. Yeah, but I'm not so sure I understand what the concept of the chapter is, of the section. Famous interpretation. Dirk's work did not provide a precise description to calculate the sum over paths, and he did not show that you could recover the Schrödinger equation. Dirk's quantum action was, for most cases of interest, simply equal to the classical action, appropriately discretized. This means that the classical action is the phase acquired by quantum evolution between two fixed endpoints. He proposed to recover all quantum mechanics from the following postulates. The probability of an event is given by the squared modulus of a complex number called the probability amplitude. The contributions of all paths in configuration space. And the contribution of a path is proportional to these, where S is the action given by the time integral of the Lagrangian along the path. Okay, so this concept of action seems to be... So in physics, action is a numerical description of a part of how a physical system has changed over time. It is significant because the equations of motion of a system can be derived through the principle of stationary action. In a simple case of single particle moving with a specific velocity, the action is the momentum of the particle. So when we talk about action, we're talking about the stuff that is changing the system. And in this case, the momentum of the particle times the distance it moves, added up along its path, or equivalently twice its kinetic energy, times the length of time for which it has... So in physics, action is a numerical description of part of how a physical system has changed over time. So kind of you'd say what's the, not to be confused with action at a distance. Yeah. Why you go ahead and use these words? I mean, it is because the equations of motion of a system can be derived through the principle of stationary action. In the simple case of a single particle moving with a specified velocity, the action is the momentum of the particle times the distance it moves. Okay. So what's quantum action? So the quantum action principle then is trying to describe numerically how the system is changed or changes. So for states with a definite energy, this is a statement of the relation between the frequency and energy, and the relation because The Hamiltonian in classical mechanics is derived from a Lagrangian, which is more fundamental quantity. That is a function of the position of momentum at one time. In quantum mechanics, the Lagrangian transform is hard to interpret. So the relation between the two is okay. So that is the action on the Hilbert space. It's funny. I have to actually search for the word action to try to understand how is this being defined here. So in quantum mechanics, a state is a superposition of different states with different values of Q and P, and the quantities P and Q can be interpreted as non-commuting operators. The operator P is only definite on states that are indefinite with respect to Q. The sum over all states integrates over all Q, and so it takes the Fourier transform to change basis. That is the action on the Hilbert space. So okay, so this function is the quantum analog of the classical action. So what is this function? Another way of saying is that since Hamiltonian is naturally a function of P and Q, exponentiating the quantity and changing basis from P to Q at each step allows the matrix element of H to be expressed as a simple function. Whoa, whoa, whoa. What did I do? What happened? I pressed something in the mouse and it just went nuts. A simple function along each path. This function is the quantum. Okay, so exponentiating this quantity and changing basis from P to Q at each step allows the matrix element of H to be expressed as a simple function along each path. This function is a quantum analog of the classical action. So what this is basically saying is that the so H being the Hamiltonian, I guess, right? So the H factor on this stuff here, right? I don't know what the Lagrangian transform here has to do, but the idea is that the H contains all the dynamical information. It pushes the state forward in time. And the first part of the last part are just Fourier transforms to change to a pure Q basis or an intermediate P basis. I don't really know, but essentially what this is saying is that this H contains all the dynamical information, but somehow what you can derive out of all these is that if you manipulate if you exponentiate this quantity and do the change basis, if you do these, then you can basically express the Hamiltonian as a function along each path. So this means you can somewhat probably decompose these. And so that's the action, I guess, the function that is defined over all the paths. The function that is defined over all the paths is what's then the quantum analog of the classical action. So it's what's yeah. So that's just telling that it's just a confirmation, or just saying that is that Hamiltonian does encode all the information that allows us to describe how the system's changed over time. I guess this is just it's been formally proved. I really don't know. And maybe this is where one starts to move from the Hamiltonian way towards the path integral way by actually realizing these. This gives the time. So there further noted that one could square the time evolution operator in the S representation. I don't know what the S representation is. State space representation. I don't know. And this gives the time evolution operator between time t and t plus 2 whatever, while in the Hamiltonian representation, the quantity that is being summed over the intermediate states is an obscure matrix element. In the S representation, it is reinterpreted as a quantity associated to the path. Okay, so you can then somehow reformulate that, and then you have a specific operator for each path, and the limit that one takes a larger power of these operator, one reconstructs the full quantum evolution between the two states. The early one with a fixed value and the later one with a fixed value of qt. So the result is the sum over paths with a phase, which is a quantum action. Crucially, Dirac identified in this article the deep quantum mechanical reason for the principle of least action controlling the classical limit. Okay? The deep quantum mechanical reason for the principle of least action controlling the classical limit. The only important part, I don't know. So, but okay, so there's something to go back to. Okay, so for some reason, that is something that allows you to derive the principle of least action, classical. Okay. So Feynman did a bit of extra work on top of these. In order to find the overall probability amplitude for a given process, then one adds up or integrates the amplitudes of the third postulate over the space of all possible paths of a system in between the initial and final states. Space-time coordinate to another, it is correct to include paths in which the particle describes elaborate curlicues, curves in which the particle shoots off in outer space and flies back again, and so forth. The path integral assigns to all these amplitudes equal weight but varying phase or argument of the complex number. So Feynman actually then built a bridge towards the Schrodinger equation, and then the path information quantum field theory represents the transition amplitude corresponding to the classical correlation function as a weighted sum of all possible histories of the system from the initial to the final state. I'll be right back. Yeah, now microphone should be back. So where are we? Okay, so basically Feynman just kind of built a bridge between these, right? So this is a bit more historical. I don't really understand all the details about these, but path integral economy. Okay, it's time slicing derivation. So one common approach to deriving the path integral formula is to divide the time interval into small pieces. Once this is done, the Trotter product formula tells us that the non-commutativity of the kinetic and potential energy operators can be ignored. For a particle in a smooth potential, the path integral is approximated by its zigzag paths, which in one dimension is a product of ordinary integrals for the motion of the particle from position xa to time ta to xb at time tb. The time sequence is like this, can be divided up into smaller segments of one fixed duration. The process is called time slicing. An approximation of the path integral can be computed as proportional to but what are we integrating? We're integrating the Lagrangian. As the classical Lagrangian of the one-dimensional system considered. In terms of the wave function in the position representation, the path integral formula reads as follows. What is that? Okay. Okay, so let's what is the Lagrangian then? So what are we integrating here? What are we integrating? Because that's something that bothers me. I don't really know what the Lagrangian is. At least not at the level I know what the Hamiltonian is, right? Lagrangian mechanics. Stationary action principle. So Lagrangian mechanics defines a mechanical system to be a pair ML of a configuration space M. Okay, and a function L, LQVD called Lagrangian. So Lagrangian is a function. By convention L equals T minus V, where T and V are the kinetic and the potential energy of the system, respectively. What are QVT? Momentum, velocity, and time. Q belongs to M, and V is a velocity vector at Q. V is tangential to M. Given the time instance T1 and T2, Lagrangian mechanics postulates that the system's trajectory, describing evolution of a system, over time is represented by a curve, must be a stationary point of the action functional. Okay, here we have this S, the thing with the action stuff. So if M is an open subset of R, and then of the real of the n-dimensional reals, and then T1, T2 are finite, then the path is a stationary point of S. Okay, so it might be actually really worth coming back to be that deep as these, right? Lagrangian mechanics. So just because I want to understand that better. So it seems like the path integral is then based on the Lagrangian stuff, not the Hamiltonian stuff. So that's based upon you're integrating a function. It's a functional integral. right? That's what it's a functional integral. So you're integrating a functional integration. Functional probability. So that might be a point worth taking a look at. Let me just bookmark these, and then Lagrangian Mechanics. And again, all I'm doing now, these first sessions, is really trying to navigate. I'm just really trying to navigate the whole landscape of, you know, all these complex things, and to try to understand complicated things, try to understand a bit where's a good point, a good anchor point to start from. Because we've gone from the project here, we got to the way they're trying to model things, and now there's the dynamic part, which they try to seem to map to the path integral formulation of quantum mechanics. And that's what led me to the path integral stuff here that basically talks about action and the quantum action, the quantum version of the classical action, and you know, being then some sort of the action that's described by each path, and the action being the amount of change that a system would be undergoing and within this path. And so if you add all these, that's the analog for the quantum system would be that you add all the actions, or you integrate all the actions, all the amount of change that goes. And I guess that some of these things can cancel out, right? Like if a path will go one way, another path will go another way, somewhat they could kind of cancel. So this integration, this addition there. But this integration then is, so this is the stuff here. Okay, so let me bookmark this as well. So we're integrating, so we're slicing the paths, and then we're integrating over this L thing. And L is the Lagrangian of the one-dimensional system. This is the Lagrangian that's then associated to that specific path, right? Yeah, that's kind of, let's try to glue some of these pieces together in a later session. That was a quick one, but at least it helped me move a little bit forward. I think that point in time where just still navigating the whole landscape is a bit complicated to make progress, but we'll get there. Have a good day.